let's go here. All right, so this looks like a question on mechanisms. This guy says the rate law for a reaction is found to be that. Which of the following mechanisms gives this rate law? All right. So let's see what we have. The first one, we identify that the slow step is the second one. So for the rate law for that one, let me make this smaller. Pop this up. Okay. All right, so for the first one, the rate law is the second step. So the rate is going to look like K times E times B. And so that doesn't look like the experimental rate law. So since there's a preceding fast step, we might be able to use that argument that we looked at yesterday. If there's a preceding fast step, then we can assume that it comes to equilibrium and the rate forward equals rate reverse. So the rate laws for those would look like, for that first fast step, oh shoot, I'm having some difficulties here. It would look like the rate forward equals the rate reverse, and the rate forward equals K, let's say 1 times the concentration of A, B. That should equal the rate reverse, which say K, I don't know, 2 times the concentration of E. And that has our intermediate in it. So I can solve for E and then replace it here and see what it looks like. So if I solve for E, I get K1 over K2 times A, B. And then the experimental, the rate law that corresponds to the slow step, which that's the one that has to agree with the experimentally determined rate law, then looks like this with that substitution. Times A B squared, right? So that is not what they give me in the problem over here. So that can't be right. So the first one's no good. The next one is the same, except now we have in the slow step A instead of B. I think that one should work out now. All right, again, we identify the slow step for that second possible mechanism. So the rate law for the slow step equals K times E times A. The preceding fast step gives me K1, concentration of A, B equals K2 concentration of E. So now I can substitute in, and when I do, I get this times A squared B. And I just renamed this K as the old K. So I should probably put an S there. KS times K1 over K2. So I'll just call that K. And so now I see there's an agreement between the rate law that second mechanism would propose and the experimental rate law. So 2 looks good. In 3, the slow step is first. So for the mechanism 3, the rate of the slow step equals some K times A squared. And since it's the slow step and it doesn't agree with the experimentally determined rate law, that's the rate equals K times the concentration of A squared times B, then 3 can't be it. So it looks like just 2 should be the answer. Any questions on
Okay,
that?
thank you.
Yeah, sure.
Yeah, so when you start, do you always want to start looking at the slow step, like in this kind of situation?
Yeah. So yesterday, I don't know if you viewed the discussion that we had, but in the discussion, there was basically 2 things that you had to make sure were true before you can say that a mechanism was possible, that it was valid, that you shouldn't throw it away. And that's all we can do. We can't prove it beyond a doubt that it's the mechanism. So the first thing is, do the steps in the mechanism add up to give the overall reaction that it's supposed to describe? Now, they didn't give us an overall reaction, so we didn't have to do that. So this is kind of easier in that respect. The second criterion is that the slow step should give a rate law that agrees with the experimentally determined rate law for it to be valid. So we go right to that for this problem and try to figure out whether that slow step gives a rate law that agrees with the experiment. Remember yesterday when we were introducing mechanisms, we were saying that the overall speed of any reaction or any process, whether it's a reaction or it's a factory assembly line, can only be as fast as the slowest step. So if we're looking at a detailed description of a reaction in the form of a mechanism, which outlines what we believe to happen at the molecular level, then we need to identify the bottleneck, because that's going to dictate how fast the whole thing can go. So that was important to identify the slow step, look at the rate law that you get from that slow step. And because these are mechanisms, we can look at the stoichiometric coefficients. Whereas remember before, when we introduced kinetics, we said, hey, there was only one way really to come up with a rate law, and that was with experimental evidence, whether it was the method of initial rates where you used a bunch of experiments with different initial concentrations, or you use the integrated rate law with the graphical method to plot and see which one came out linear, see how that reaction concentration was behaving in time, and then associate it with the integrated rate law. That was the only way. You needed experiment. But with mechanisms, you have to assume that they're true until proven otherwise. So that's your job. Your job is not to make up mechanisms. Your job is to analyze them and see if they're possible. So that was kind of a long-winded answer to your question. I don't know if it answered it or not.
Yeah, thank you. That cleared it up so much. It makes sense now.
Yeah, sure. Is there any other question on that or anything else before we go on to 21 and take a look at that? All righty. Okay, 21 looks like another one. Let's see. Consider the following mechanism. If we assume the second step of the mechanism is the rate determining step, so that must be the slow step, and the first is a fast equilibrium step, which of the following rate laws is predicted by this mechanism? Okay, so they're going to have you go through those two criterion that we were talking about, mainly that the slow step gives a rate law that agrees with one of these guys down here. So I don't think I'm going to do this for you, but I'll get you started on it. Okay, so we have a slow step in our second step. So as soon as you see this in a mechanism, unlike what we're used to before when we look at the overall reaction, and this time this is the overall reaction. This is what you guys have been looking at in your chemistry career with the stoichiometric coefficients. This is where we say, oh, well, the rate law doesn't necessarily have to agree with these stoichiometric coefficients up here in the overall reaction, this one. But over here in the mechanism, then yeah, we can look at those stoichiometric coefficients and see what the rate law is going to be right off the bat. So the second step, which is the slow step, gives a rate law that looks like this, where we have O3, ozone, to the first power times an oxygen atom to the first power. And so I don't see any of those in the choices. But you can't throw this away right away because there's a fast step that precedes this that reaches equilibrium. So you kind of have to do the same song and dance that we did on the other problem that we just looked at and see if we can substitute out the intermediate. Can anybody pick out the intermediate in this mechanism?
Would it be oxygen? Just O.
Yeah, you're right. It's the oxygen atom, right? So in this mechanism, what's O3?
The reactant?
It's a reactant. And what's O2?
The product?
Yeah. And so an intermediate is defined as something that's produced, but then consumed in a subsequent step. And intermediates are hard, like we were talking about yesterday. They're hard to get a handle on experimentally because they just don't hang around long. So you won't find them in these experimentally determined rate laws. So there's a way to rationalize why it's not in one of these possibilities down here. And so you have to do that thing that we just did previously and that we exemplified in our discussion yesterday. Does anybody want me to go ahead and finish this, or are you good at that with that? Okay, so no one wants to finish. You want to try it on your own? All right, that's good. Any other questions that you want to look at? All right, no other questions? All right, we're in good shape then. And I think now we're ready to take a look at the equilibrium. So this is the next chapter, equilibrium. I have these fancy schmancy arrows here. And as you know, I think from Chem 200, you studied equilibrium a little bit. And here's a picture of an equilibrium. So we start off with some N2O4, and we put it in a container, and then it degrades naturally and spontaneously, and it starts to produce some NO2. And so that clear sample becomes slightly brown, and then it gets a little deeper with brown, and then it doesn't change anymore. So this is said to reach equilibrium. One of the definitions of equilibrium that we've used in kinetics, as you recall, is that the rate of the forward reaction has to equal the rate of the reverse reaction. And when that happens, this is called equilibrium, and the concentrations of the reactants and the products cease to change. So in other words, if I balance this chemical reaction, I have to put a 2 here, right? So now it's balanced. So at equilibrium, for every 1 N2O4 that reacts and makes 2 NO2, 2 NO2 get together and make 1 N2O4. So you see the concentrations don't change anymore. But this is called a dynamic equilibrium. That refers to the fact that the reactions are still taking place. It's just that they're taking place at the same rate. Any comments or questions on that? All right, then we can take a look at this plate. And we're going to consider just some generic reaction of A going to B, and then its back reactions, B going back to A. So say they're both first order, and it doesn't matter for the sake of argument, but we can imagine that the rate law could look like this for either one of those reactions, forward and reverse. So we know that at the start, we have some concentration of A, so there's only a forward reaction. Why? Because there's no B. B is 0, and anything times 0 is going to give you a rate of reverse of 0. But as the reaction takes place and we start making some B, then that back reaction kicks into gear until we get to a certain point where the rate forward equals the rate reverse. And at that point, those two equations are equal. So we can write this equality down here, and then we can clear the concentration terms on one side of the equation and the rate constants on the other, and say, oh, well, geez, at the situation of equilibrium, if I take a ratio of the concentrations, then obviously that has to be a constant. And so that's the first thing we notice about this special life time or special point in a reaction life where the rate forward equals rate reverse, and we call that equilibrium. So the ratios of the concentrations which cease to change at that point in time should equal a constant. So all of that, I think, should kind of make sense. Here's a picture of this dynamic equilibrium. And sometimes we refer to this picture here as the kinetic region, where the concentrations are changing. And then once they reach a constant in time, this is known as the equilibrium region. So the concentrations of A, the reactant, decrease in time until it reaches equilibrium, and there's a constant. The concentration of the product B increases in time until it reaches equilibrium. In this picture, we see that at equilibrium, there's more A, more of the reactant than B. Is that always the case? You got a 50-50 chance, yes or no? Yeah. Yeah, of course not. No. You know from Chem 200 that some reactions are near completion reactions, right? So like combustion reactions or acid-base neutralizations. So your reactant concentrations can go almost down to zero, while the product concentrations go above that somewhere. So this is just an example. This isn't always the case, which I think kind of hints towards a big purpose of studying equilibrium and all the aspects that go along with it. Because in Chem 200, you guys mostly dealt with reactions that went to completion. For example, do you remember when you had problems and they said this many grams of this reactant reacts with this many grams of this reactant, how much of this product is produced? You guys remember that kind of problem?
Yes.
Yeah. What do you remember what they are called?
Is it like the ones with the where you had to find the limiting reactant?
Yes. Brilliant. That's exactly correct. They're called limiting reagent problems. So you assumed that you ran out of one of the reactants, and that dictated how much of the other one was used and how much it was left. It also dictated how much products you made, right? You remember that?
Yes.
All right. Um, Now, what are you going to do when you deal with most of the reactions in chemistry that aren't completion? They actually reach equilibrium. You can't use limiting reagent approaches anymore to find out what's left, right? You're screwed. So the purpose of this chapter is just that. For the vast majority of reactions in chemistry that don't come to completion, how are you going to find out what you're left with? You have to study equilibrium techniques. And so that's what we're getting at. But we're still crawling before we can walk. So we're just getting used to some of the definitions and the concepts and the ideas of what's happening. All right, the next plot has a rate versus time, and it shows you that the rate backwards is going to be zero because there's no product concentration. So any constant times zero is zero. But as that concentration increases, as the rate goes through that kinetic region, you see that those two rates forward and the rate reverse are approaching until they equal. And that's what equals at equilibrium. It's not the concentrations that are equal. So get that out of your head and don't ever assume that. It's very rare that you have at equilibrium a 50-50 mixture of the reactant and product. It does occur. In fact, there's a special name for it. It's called a racemate. It's a racemic mixture, but we'll save that for later in the course. It's very rare. Okay, moving right along, we take a look at this reaction, the production of ammonia from nitrogen and hydrogen, called the Born-Haber process. And we're going to think about that in terms of equilibrium. So we can start with a mixture of the reactants in any proportion, and we just leave that reaction go, and in time, it's going to reach what's called equilibrium. Now, it turns out that all reactions go towards equilibrium. And in fact, everything in the universe goes towards equilibrium. And we're going to study the energy criterion for why this takes place when we look at thermodynamics in an upcoming chapter. But we can assume right now that everything is going towards equilibrium. When I was taking this class, my professor said, hey, listen, old chemists never die. They just reach equilibrium. So that's what we're heading for. We're all heading for equilibrium. So anyway, we can start our equilibrium journey with all reactants, and it comes to equilibrium. And at that point, the rate forward equals rate reverse. The concentrations of reactants and products are constant. They don't change anymore. And we can form a ratio of concentrations and know that that's going to be a constant. So what does that mean? That means that even if I started with all product and no reactants, and I put it in a container and I left it go, in time, it's going to reach equilibrium with what I defined as my reactants. And at that point in time, the concentration ceased to change. And if I take a ratio of those concentrations, it equals the same as the other case when I started with just all reactants. So that's kind of important to realize that, right? Okay, so that's the statement of what happens. Here's a nice picture again that explains kind of what I'm trying to convey. And it says, okay, let's take a look at this first plot here where we start with all reactants. So I have some hydrogen here and I have some nitrogen. I don't have any of the product ammonia. The reaction goes through the kinetic region. It reaches equilibrium. Once I have those concentrations at equilibrium, they cease to change. I can figure out what they are, put them in a ratio, and I get a constant. What's that mean? That means that if I started with any other mixture, including all reactant and no, all product and no reactant, or anything in between that, and I left that container go, it's going to change until again it reaches equilibrium and the concentrations are constant, and I can form that ratio again, and that ratio is going to equal the same as it did up here. That's not saying that the concentration of hydrogen down here has to equal the concentration of hydrogen up there or any of the others. What it's saying is the ratio has to equal. Just like 6 over 2 equals 3, and so does 9 over 3. It's the ratio that equals the same constant, not necessarily the actual concentrations. So I just point that out because that's a common misconception, and that can get lost. That tree can get lost in the forest if you don't point it out. Any questions on this so far? Okay. Now, this slide is probably one of the most important slides in this set because it defines what everybody in the world understands as the equilibrium constant. And it's defined by this weird thing called the law of mass action. And what the law of mass action says is if you have some reaction that's at equilibrium. So we're used to looking at generic um, reactions where small a is the stoichiometric coefficient and big A is the molecule or atom or whatever's reacting, and so forth. Now, once this reaction comes to equilibrium, we say the rate forward equals rate reverse. Sometimes that's signified by an arrow this like that, and then one like that, or arrows both ways. What the law of mass action does for us is it defines what the equilibrium constant means. So here's what we're using as the equilibrium constant. It's big subscript C, meaning concentration equilibrium constant. Using the law of mass action, it's defined as, or it equals, I can put another line there and say it's defined as, or it equals the concentrations of the products to their stoichiometric coefficients divided by the concentrations of the reactants to their stoichiometric coefficients. So this defines the equilibrium constant for us, and this equilibrium constant is called Kc because it uses concentrations in units of molarity. So this is our default equilibrium constant. It's what we call K. If you don't see a subscript C, then you assumed it's Kc. So this is the most common equilibrium constant. But there's other ones that we're going to look at like Ka, Kb, Kf, Ksp, and Kp. But this is the most common one. And when you see an equilibrium constant and it doesn't have anything there, you can assume that it's Kc, and it was formed by using the concentrations of the products in molarity to their stoichiometric coefficients divided by the concentration of the reactants in molarity units to their stoichiometric coefficients. Now, since these stoichiometric coefficients will change the number of units of molarities because they get squared or cubed or whatever that stoichiometric coefficient is, it turns out that equilibrium constants are unitless. So they don't have units. The equilibrium constants themselves don't have units. How to form them, though, they do. So this part has units. The equilibrium constant itself is unitless. For example, this specific reaction that we looked at before with the clear going to the brown has a stoichiometric coefficient here. Now, as soon as I write down this reaction, I define what I'm going to call my reactants, and I define what I'm going to call my products. So when it's written down, I can use the law of mass action to define the equilibrium constant for that reaction. Any questions on that? All right. Now, for obvious reasons, the equilibrium constant is also temperature dependent, right? Because if you change temperature, you know K's change, the rate constants, the small K's, and you know that that ratio is going to change, and that that ratio is proportional to the equilibrium constant, which is a ratio of the concentrations. So these equilibrium constants are also temperature dependent. Okay. This is the second equilibrium constant that you're going to look at, Kp. It's for gas, and it's formed in the same way as Ka, but now we're going to use units that are particular to gases, which is atmospheres. So, for example, in this case where I have A going to A plus B going to P and Q, Now for this guy, if I want to form Kp, which is in pressure units, each one of these terms here refers to a reactant or product in units of atmospheres to their stoichiometric coefficients. Okay, but you see, we still have the partial pressure of P, which is a product, to P, which is the stoichiometric coefficient, times a partial pressure of Q in units of atmospheres to its stoichiometric coefficient, and so forth for the two reactants. Any questions on that? All right, now how are Kc and Kp related? Well, they're related using the ideal gas law. Remember, the ideal gas law is PV equals nRT. So if I take N, divide it by V, that's moles per liter. That's a concentration. So that's what they do down here. They substitute that in, just call it M for molarity. And now we see that P equals some concentration with this factor of RT. So it turns out that Kp is related to Kc with this factor of RT to what's known as delta N, or the change of the number of moles of gas in the reaction. Because gas for Chem 201 is the only thing that really exerts pressure or has changes in pressure. The conditions that we need to experience those kind of changes for liquids and solids, we don't consider. So we only have to worry about gases. Now, if the reaction involves no gas, or there's the same number of moles of gas for the reactant side as the product side, then this term is a 1. Because anything to the 0th power is 1. Any questions on that? Okay, let's take a look at an example of applying that, and then maybe you'll have a question. So here we have our Born-Haber process, the making of ammonia. They tell us the equilibrium constant is 9.6 at 300 degrees Celsius, and they ask for Kp. So I know I could put Kc here. I know what R is. R in this case is going to be the 0.0821 liter atmospheres per mole K. Temperature is going to be that temperature in Kelvin. So I have to make that conversion. And delta N is going to be the change of the number of gas molecules. And so we normally calculate deltas as final minus initial. So it's the products minus the reactants for this delta definition. We got products minus reactants. I have 2 moles of gas on the product side, and 3 plus 1 is 4 moles of gas on the reactant side. So I get a delta N of minus 2. So that goes there. I convert that Kelvin, that Celsius to Kelvin, and I can calculate my Kp value from my Kc value. All right, so that's just some definitions and a little bit of mathematical manipulation. I don't think that it's really heavy in the concept area, but let me know if you have any questions. All right, moving right along. So we're getting comfortable with the definitions of equilibrium. Now we want to maybe look at some of the lingo that you're going to run across when dealing with problems in the homework or exams or in lab dealing with equilibrium. So again, we go back to this generalized equation as say A goes to B, it reaches equilibrium. We can calculate a K, and the K is defined using the law of mass action. And that says take the concentration of the products to their stoichiometric coefficients, which is 1 in this case, and the reactants to its stoichiometric coefficient, which is 1. And it says down here, we can use the magnitude of Ks because you're going to need to understand and look up these values for Ks for different experiments and be able to use them. What are you going to use them for? You're going to use the equilibrium constants to allow you to calculate the concentrations of the reactants and the products at equilibrium. Remember, you can't use limiting reagent techniques anymore. So now you're going to use this thing called the equilibrium constant, and it's going to have a value. For example, I think this one up here, let me write HCl plus H2O goes to H3O plus Cl minus. The equilibrium constant for this is going to be around 10 to the 6. Okay. Now that's going to be very different than another equilibrium constant. Let's say this one, HF. Let me erase that. Put it right here. HF plus H2O goes to H3O plus F minus. Here, the K for this is going to be around 10 to the minus 4. So the magnitude of the equilibrium constant tells you, by just looking at it, tells you the relative amount of reactants to products that you can expect. And for example, you're going to be able to look up these values in your textbook or online in tables of equilibrium constants. We haven't shown you how to do that yet, and we haven't shown you how to use the equilibrium constant. We're just getting used to the idea right now. And a lot of people say, well, you got to look at the magnitude of that equilibrium constant, because by one glance at that number, the magnitude, the value, you can tell the relative mixture you would expect at equilibrium. And I'll ask you, for that first reaction with HCl that has an equilibrium constant of 1,000,000, would you expect more products at equilibrium or more reactants?
More products.
Yeah. And why would you expect more products? Because of the way the equilibrium constant's defined. It's defined as the concentrations of the products to their stoichiometric coefficients over the concentration of the reactants to their stoichiometric coefficient. So just by looking at that number, you can tell pretty much what you're going to have mostly in that case at equilibrium. So just looking at the magnitude, we can tell what we're going to have mostly of. And in this case, it might be a surprise to you for this guy that when it reaches equilibrium, you're left with mostly HF. So here we say the equilibrium lies to the left towards HF. And in this case, the first one, we say the equilibrium lies to the right towards Cl minus and H3O plus. Okay. And so that's some of the lingo that you're going to have to be familiar with. Any questions on that? Lying to the right or the left? Okay. Here's a nice picture of what we mean by that. When the equilibrium constant is much greater than 1, like 1,000,000, we get mostly products. When the equilibrium constant is less than 1, like 0.0004, right? Or whatever, then in this case, we're going to be left with mostly reactants when that reaction reaches equilibrium. Any questions on that? All right. Let's go back to that example that we were looking at before of the clear to the brown. This is balanced now. Once I write down that reaction, I can define the equilibrium constant that goes for that reaction. And I can either go to the lab, calculate those, or experimentally determine those concentrations and find this number, or I could look this number up in your textbook or online. Now, you have to compare equilibrium constants to the same temperature equilibrium constants. Otherwise, they're going to be different. So you have to remember that equilibrium constants, like rate constants, small k, are temperature dependent. All right, now, what if instead of writing this reaction like this, I flipped it around and I said, oh, I want to consider this reaction where I take 2NO2 and that goes to N2O4. Is the equilibrium constant the same? No, it's not the same. It's defined differently by the mass of law action, the mass of the law of mass action. Wow. So this Kc here is not equal to this one, not equal, but they should be related, and they are related. Look at the definition. This has N2O4 on the top, where this guy has it on the bottom. This has NO2 squared on the bottom. This guy has it on the top. So you can easily see that they're inverse of each other. So when you flip the reactants and products of any reaction, the K changes, but it changes in a predictable way. It's 1 over the unflipped version. So if I need, essentially what we've done is we've taken all the tabulated data in your textbook and just cut it in half. If you can't find the K for this reaction, but you can find it for the reverse reaction, then you can calculate the K that you need. Any questions on that? All right, I think this is, we're just getting going here, just taking our time, introducing some of the definitions, and playing with this concept of the equilibrium constant. Okay, now we're going to take a look at another interesting feature of the equilibrium constant, and that is whenever we form equilibrium constants, strictly speaking, by definition, we have the concentration of the products to their stoichiometric coefficients over the concentration of the reactants to their stoichiometric coefficients. But whenever one of the reactants or products is a solid or a pure liquid, its concentration does not change. And so what is done in the textbooks and online is that we take that constant and you know, if it's on the bottom, then we can times it by that constant on over here on the top, and then times it over here, and then just call this the new constant. And that's the one that you're going to find in the textbooks. So it already includes these constants in the equilibrium constant. And this happens whenever a reactant or a product is a solid or it's a pure liquid. Okay. So this shows here a reaction with two solids, and the equilibrium constant, therefore, for this guy equals the concentration of CO2. And that's it. This and this are already incorporated into that constant because they are constant. They don't change. For example, if I take a beaker and I put in some lead iodide solid, I know that's fairly insoluble, but some's going to dissolve to lead 2 plus and 2I minus. And in the process of that dissolving, I might lose some of this solid right here. So I don't have as much solid that I started with, but it comes to equilibrium fairly quickly. So what is the concentration of this solid? The concentration can be found from the density, which let's say is in units of grams per liter, divided by the molar mass, which let's say is in grams per mole. So the grams cancel out, and I get per concentration, this is the concentration of that solid, the concentration of the solid equals moles per liter. So it's the density divided by the molar mass. And you have to ask yourself, during that reaction, does the density of the solid change? Anybody know? So the solid is down here. I lost some of it, so the amount changes. Does the density change?
No.
Correct. You're good. So yeah, the density doesn't change in the solid. There's less of it. Does its molar mass change? No, it doesn't. It's still whatever solid it was, which in this case was lead iodide. So its concentration doesn't change, and it can be incorporated into the equilibrium constant, and that's what's done. And you should understand that whenever you're dealing with a reaction with a solid or a pure liquid. Now, what do I mean by a pure liquid? Let me go back to one of those reactions that I was looking at before. Let's do the HF plus water goes to these guys. This is a pure liquid. This is aqueous. Aqueous and aqueous. You're familiar with this terminology. So for this equilibrium, K, we would define this as H3O plus F minus over HF. No H2O. It's already in here. And the reason is because it's a constant. Okay, look, this reaction is in aqueous conditions. It's mostly water. So if we use up a little bit of water, it might go down a little bit, but seriously, it doesn't change all that much, so it's taken constant. Any questions on that? Okay. So again, just to recap, if I want to find or define the equilibrium constant according to the law of mass action for this reaction, it would equal this Kc equals CO2 gas in units of moles per liter. This is not Kp, it's related to Kp. If I wanted to calculate Kp, I could take the Kc and multiply it by RT to the delta N, but I see delta N is 1 minus 0, it's 1. Any questions on that? So you have to watch out for solids and pure liquids. All righty, you guys ready to do an equilibrium problem? Or do you need to do a couple one-arm push-ups?
I think
I couldn't hear you, sorry. I know someone was out there going to say something, but you got cut off. I'm sure it
What
was.
would be another example of a pure liquid?
Oh,
Or is it just water?
yeah, for Chem 201, that's pretty much all we deal with is aqueous solutions. But you can do reactions in other solvents, like some sort of a gasoline type solvent or an organic solvent, where you get rid of all of the water because water's bad for this particular reaction. So it could be methanol, could be a pure liquid if you do it in pretty much methanol solution. I've seen that before. Some alcohol or some organic compound, like a gasoline type, octane. But we don't deal with anything but water in Chem 201. Any other questions? All right, let's introduce our first equilibrium problem, ladies and gentlemen. This is what I call type A equilibrium. It's pretty much a no-brainer type equilibrium problem. It's a plug and chug, so you guys will like this. We're just using some definitions. So in the problem, it gives us a temperature. And we got to know what temperature it is just because that's the equilibrium constant we're calculating. If it's at a different temperature, then it's going to be a different equilibrium constant. So you should always state or always look for a temperature. In fact, your textbook tabulates values for K at 25 degrees Celsius. That's what you're going to find. You're going to find them at room temperature mostly. But anyway, this problem says at this temperature, this reaction has come to equilibrium, and somebody did the experiment and found what the concentrations of all the components in the equilibrium reaction are. So this reaction comes to equilibrium. We use our definition of the equilibrium constant, the law of mass action, which says that Kc, concentration of the product to the stoichiometric coefficient, over the concentration of the reactants to their stoichiometric coefficients. We see what the experiment found, and we just plug and chug. We put those numbers in and put them in our calculator, and we calculate the equilibrium constant. Pretty straightforward. All righty. Now, what's coming up, I dissected into two different categories called type B and type C equilibrium problems, both of which are best solved using what's called an ice table approach. It's just an approach that allows you to organize the data that you're given and make the relationships that you need to make. For example, the type B equilibrium problem gives you initial concentrations of all the reactants and products, and then one of the concentrations at equilibrium, and asks you to calculate the equilibrium constant. Type C gives you the equilibrium constant and asks you, along with initial conditions, and asks you to calculate equilibrium concentrations. And so that's essentially all the possible types of equilibrium problems you guys will face. So I just divided them into the easy ones, like type A, and the ones where you need to, I think, learn the ice table approach for organizing your data. And I can't emphasize this enough, because when we go on to the next chapter and chapters after, when you have to use equilibrium constants, you're going to be relating the equilibrium constants not only to the concentrations of the reactants and products, you're also going to be relating them to things like percent ionization, pH of the solution, at the point at which precipitation takes place. And to do all these different concepts, you need to make connections. And to make those connections clearer, it's really good to learn this ice table approach. So I can't emphasize that enough for this section. But anyway, on to type B equilibrium problems. And here you can read this. I'm not going to read it to you, but it kind of explains what's going on with this type B equilibrium problem, where you're given initial conditions and one concentration at equilibrium and asked to solve for the equilibrium constant. Okay, that's essentially what type B is. So how do you do it? You use an ice table. It explains what the ice table is, but I like to explain it by just looking at a problem. So here we have example 1 of this. We place 2 moles of this compound in enough water to make that volume so you can calculate its concentration. Remember, these equilibrium constant, when we're not talking about which particular type, you assume Kc. Okay. At equilibrium, we find that there's 0.66 molar NO. So what's K? So the ice table approach says, all right, I have my reaction. Okay. What I want to do is I want to, underneath each one of these guys, I'm going to make a table, an ice table, an ICE. Sometimes this C, you'll see old timers like myself put a delta. It just means change. Okay. So you have initial, change, and equilibrium conditions. And now in this ice table, you read the problem and you try to fill out what you know from the problem, fill out the different spots in the ice table. So it says that I have 2 moles in 1 liter. That's 2 molar initially of my reactant, NOCl. It doesn't mention anything about the products, So you have to read between the lines in these equilibrium problems and say, well, geez, they didn't say anything about it. Let's assume there's none there. So you have 0 initially for the products. Okay, you read on. At equilibrium, we find 0.66 molar NO. So that goes in this position here, 0.66 molar of NO at equilibrium. What is the equilibrium constant? Well, okay, I can define what the equilibrium constant is in terms of the law of mass action. And once I do that, I can see which values in the ICE table I'm going to need, because then it becomes, can't forget that too. Then it becomes a type A problem. So what I need from this ICE table, they gave me this guy at equilibrium. I need the NOCl at equilibrium and the Cl2 at equilibrium, and then I can form K and answer the question. So how do I do that? The secret is in the change column. And that one that they give you. And they only need to give you one at equilibrium, and it doesn't matter which one. It could be a reactant or it could be a product. Just one. That's all you need. And experimentally, that's usually what you do. You just solve for one concentration of the reactant or product, and then you can deduce what the others must be at equilibrium. And you can do this because we know what happens at equilibrium. And we can go back to that definition real quick. We know that for every 2 of NOCl that react, I make 2 of NO and 1 of Cl2. But when that happens, every 1 Cl2 that I make has to be used. And for every every 2 NO that I make, 2 have to be used in the back reaction to make 2 NOCl. That's equilibrium. So the stoichiometric coefficients can be used to deduce what the change must have been. So it started out with 0, and I produced 0.66 molar. So the change of this must be 0.66 molar. All right. And I can figure out what the change of all the other ones are as well. So I see that there's a ratio of, get out of here, go away. Sorry about that. So I see that there's a 2-to-2 ratio. So I know that this guy has to be 0.66 as well. And now there's a 2-to-1 ratio. So what does the Cl change have to be? Anybody?
Would it be 0.33?
Yeah, you're right again. Right. So those stoichiometric coefficients allow you to calculate the change of the others. And then from those changes, you can figure out what the equilibrium concentrations must be. So this is 4, 3, 1. And now it becomes a type A equilibrium problem. I just take those equilibrium concentrations, plug them in the K, and solve for my equilibrium constant. Any questions on that? So you'll be looking at those in homework. And also you're going to be looking at this. Well, this is another example of the type B equilibrium problem. Let's go through this, and then we'll save the type C for next week. I'll just push off this homework. I think it was supposed to be due on Sunday. Let's just push it off to Tuesday night. So that'll give us a chance to look at some stuff before you have to go. I mean, even Wednesday night, we can push it off too. I don't care. But anyway, let's take a look at this one. This is the second example of the type B equilibrium problem. Again, they give you a whole bunch of information and they ask you to calculate K, the equilibrium constant. In that information, they give you, or you are to assume what those concentrations are initially. So they give you this concentration. They give you this concentration. They didn't say anything about that, so you assume that it's 0. And in the problem, they give you 1 at equilibrium, and it doesn't matter which one. Once you have that, you know what its change must be. Okay. Also, I haven't mentioned this, but you also assumed back in this problem, in the change column, the signs. I didn't mention it before, right? Since we started out with no products, then for this reaction to reach equilibrium, we had to produce some products. So you knew that in the change row, underneath the underneath the products, there had to be positive signs, and underneath the reactants, we had a negative sign. And that's because of which way the reaction had to shift to reach equilibrium. This is more equilibrium lingo. Given certain conditions, starting conditions, which way does a reaction shift to reach equilibrium? That's an important question, because the answer to that question is going to allow you to assign the sign of the change in that change row for each of the reactants and the products. All right, good. So I'm glad we caught that. So again, for this example, we had 0 products. So right away, I know the change has to be plus underneath the products and negative underneath the reactants. They gave me this one here at equilibrium. I use that to find its change. And then I use the stoichiometric coefficient relationships to see what the other changes, their magnitudes, had to be. And you can calculate those magnitudes thinking in terms of what you did in Chem 200, like we did down here for those 2 different reactants as related to what the change of the product was. So I have the change of the product. How does that let me know how much the reactants had to change? I use their stoichiometric coefficients and I find their changes. So you see, this is nothing different than what you did in Chem 200. Once I find those changes, then I can add up the first 2 rows to get the equilibrium row. And again, it becomes a type A equilibrium problem where you define the K using the law of mass action, and then you plug in the equilibrium concentrations. Notice K, sometimes we put the C in, sometimes we don't. The concentrations are in units of molarity, and these aren't any concentrations. These refer to the equilibrium concentrations because we're forming the equilibrium constant. But you'll never see this because it's assumed. Whenever you say K, that's equilibrium constant, so these concentrations have to be at equilibrium. Okay? That's different from Q, the reaction quotient, which doesn't have to be at equilibrium, and we'll save that discussion for next time. what I want to ask you now is there any questions on anything that we talked about today, or lab, or scheduling, or anything? And I'm going to stop our video and discussion now. And I'm just going to wait for everybody to split or ask me a question.
Professor,
Yes.
so